So in this video, we're going to be taking a look at a problem that involves two concentric cylinders, and we are given the velocity profile of the fluid in between these two cylinders in the angular direction. We are also given the shear rate and cylindrical coordinates, and what we want to do is find the relation between the inner and outer cylindrical surfaces and the torque that is acting on these surfaces. So we have an outer cylinder and an inner cylinder with fluid in between and a mixer inside the inner cylinder that is spinning. And so if we were to take a look at this from a bird's perspective, we have the outer cylinder, the inner cylinder. So the outer cylinder has an outer radius, and the inner cylinder has an inner radius. And we know that the fluid in between the two cylinders is moving with a velocity, and we are given this velocity profile that is defined as omega, which is the angular frequency in radians per second, times k squared divided by 1 minus k squared. So this k value is just the proportion between the outer and inner radii. And so basically what this k tells us is that if we have k multiplied by a, let's say, capital R, that is going to equal the inner radius. So this capital R here is the outer radius, and this lowercase r subscript I is the inner radius. So going back to our definition of the velocity profile, it's k squared divided by 1 minus k squared times the quantity of capital R squared divided by lowercase r minus lowercase r. So again, this capital R is just the outer radius, and this lowercase r is our independent variable. So if we were to look at the velocity at any point in between these two cylinders, the radius is going to go in for this independent variable here. So be careful not to confuse the independent variable with the inner radius. The inner radius has a subscript I. So if we wanted to find the velocity at the inner radius, we would have the angular frequency times the proportion squared divided by 1 minus the proportion squared times the quantity of the outer radius squared divided by the inner radius minus the inner radius. And so using what we know about this proportion here, we can substitute the proportion with the inner radius divided by the outer radius. So plugging this in for our proportion, we have the angular frequency times the inner radius divided by the outer radius squared divided by 1 minus the inner radius divided by the outer radius squared times the quantity of the outer radius squared divided by the inner radius minus the inner radius. And further simplifying this, we have the angular frequency times the inner radius squared divided by the outer radius squared divided by the outer radius squared minus the inner radius squared divided by the outer radius squared times the quantity of the outer radius squared minus the inner radius squared divided by the inner radius. And if we were to cancel out our similar terms, the 2 outer radius squared cancels, and the 2 outer radius squared minus inner radius cancel, and the inner radius in this denominator here cancels out with one of the inner radius in this numerator here. And so that's going to leave us with the velocity at the inner radius is equal to the angular frequency times the inner radius. And again, going back to this proportion we have here, the inner radius just equals the proportion times the outer radius. So that means that the velocity at the inner radius is the angular frequency times the proportion between the inner and outer radii times the outer radius. So if we were to take a look at the velocity of the outer cylinder, we would follow a similar process. So that's going to give us the angular frequency, going back to this velocity profile we were given here, times the proportion between inner and outer radii squared, divided by 1 minus the proportion squared, times the outer radius squared divided by the outer radius minus the outer radius. And if we simplify this, this is going to give us the angular frequency times the proportion between the inner and outer radii squared divided by 1 minus the proportion squared times the outer radius squared minus the outer radius squared divided by the outer radius. And this quantity here is going to give us 0, making the velocity at the outer radius equal to 0. So in defining and seeing what the velocities at the inner and outer radius are, we can see that the inner radius is spinning, the inner cylinder is spinning, and the outer radius, the outer cylinder, is stationary. So basically what that means is there's a force that is spinning and causing the inner cylinder to move, but that means that there's also a force that is keeping the outer cylinder stationary. So if you think of when you're baking a cake and you have a mixer in a bowl, if you don't hold on to that bowl, it's going to spin along with the mixer. But if you have a force, whether that be your hands or whatever, holding the bowl still, then the bowl doesn't spin with it. So that's essentially what we have going on here. So using this information, we're going to move on to the shear rate. So the big ideas that we have going on here are 2 cylinders, and velocity at the inner radius, as we defined over here, is the angular frequency times the proportion between inner and outer radius times the outer radius, and velocity at the outer cylinder is equal to 0. So in our problem statement, we are also given the definition of the shear rate in cylindrical coordinates. So we are told that that is the radius times the derivative of the velocity divided by the radius with respect to the radius. So again, just a reminder, the velocity profile is the angular frequency times the proportion between inner and outer radii squared divided by 1 minus the proportion squared times the quantity of the outer radius squared minus the radius, or divided by the radius minus the radius. So given what we know, let's see if we can get the shear rate in terms of the angular frequency and proportion and radius that we have over here. So if we break it down, we have first the velocity divided by the radius. So if we start there and we divide both sides of this velocity profile by the radius, we have the velocity divided by the radius is equivalent to the angular frequency times the proportion between inner and outer radii squared divided by 1 minus the proportion squared times the quantity of the radius, outer radius squared, divided by the radius squared minus 1. And where we get that from is dividing this quantity by not 2, but the radius. So now the next portion we have is this derivative with respect to r. So we're going to take the derivative on both sides. And the angular frequency as well as the proportion between inner and outer radii squared divided by 1 minus the proportion squared is constant, so we can take that out front and take the derivative of this quantity here. So that's going to be the derivative of the outer radius squared divided by the radius squared minus 1. So taking the derivative of that, we are left with the angular frequency times the proportion between inner and outer radii squared divided by 1 minus this proportion squared times the quantity of negative 2 times the outer radius squared divided by the radius cubed. Now what we have to do is add in this final multiplication radius. So we're going to multiply both sides by the radius. So that leaves us with the angular frequency times the proportion between inner and outer radii squared divided by 1 minus the proportion squared times the quantity of negative 2 times the radius, outer radius squared divided by the radius squared. So what we have here is the shear rate at any position between the two cylinders. So using this shear rate, let's see if we can find the shear rate at the inner cylinder. So that's going to be the shear rate at the radius equal the inner radius. So we're going to just plug in the inner radius for this radius here. So that's going to give us the angular frequency times the proportion between the inner and outer radii squared divided by 1 minus the proportion squared times the quantity of negative 2 times the outer radius squared divided by the inner radius squared. And if we move to simplify this, we're going to use the knowledge that the inner radius is equal to the proportion times the outer radius, as we defined earlier. So we're going to plug the proportion times the outer radius in for the inner radius. So that's going to leave us with the angular frequency times the proportion between inner and outer radii squared divided by 1 minus the proportion squared times the quantity of negative 2 times the outer radius squared divided by the proportion times the outer radius squared. So that's going to leave us with the angular frequency times the proportion squared divided by 1 minus the proportion squared times the quantity of negative 2 times the outer radius squared divided by the proportion squared times the outer radius squared, and we can cancel out these like terms, so canceling out the outer radius squared and the proportion squared, that's going to leave us with the shear rate at the inner radius equals negative 2 times the angular frequency times, or divided by 1 minus the proportion squared. So that's the shear rate at the inner cylinder. Now let's see if we can find the shear rate at the outer cylinder. So similar to what we did earlier, we're going to plug the outer radius in for the radius here when we identified what the shear rate at any position was. So that's going to give us the angular frequency times the proportion between inner and outer radius squared divided by 1 minus the proportion squared times the quantity of -2 times the outer radius squared divided by the outer radius squared. And so we can cancel out this outer radius here, and that's going to leave us with the angular frequency times the proportion between inner and outer radii squared divided by 1 minus this proportion squared times -2. So bringing the -2 out front and simplifying it a bit, we are left with -2 times the angular frequency times the proportion between inner and outer radii squared divided by 1 minus this proportion squared. So we talked a little bit about the velocity at the inner and outer cylinders and the velocity profile, and then we talked about the shear rate. So how does this relate to torque? Well, there's a few steps to get to that. So knowing the shear rate is very helpful because we can use the shear rate to find the shear stress. Shear stress is defined as tau, and it is the viscosity times the shear rate. And this is according to Newton's law of viscosity. And so, keeping that in mind, let's take a minute and talk about what torque is. So torque is defined as force times the radius. So we know the radius because we're going to be looking at the radius at the inner and outer cylinders, but we don't know what the force is. But we can further break down the force to be the shear stress times the area. And again, this is shear stress, and this is area. And so area can be broken down into 2 pi times the radius times the height. And so this looks a little messy with all the arrows and the definitions of what variables means what, but basically we can use the shear rate to find the shear stress, and we can use the shear stress to find the force, and we can use the force to find the torque. So keeping all that in mind, and keeping in mind that all these previously defined equations, we are going to rewrite the important ones up here. So at any position, the shear rate is equal to the angular frequency times the proportion between inner and outer radii squared divided by 1 minus this proportion squared times the quantity of -2 times the outer radius squared divided by the divided by the radius squared. And we also defined that the shear rate at the inner radius is the -2 times the angular frequency divided by 1 minus the proportion between inner and outer radii squared. And we define that the shear rate at the outer cylinder, at the outer radius, is -2 times the angular frequency times the proportion between the inner and outer radii squared divided by 1 minus the proportion squared. Those are the formulas that we just worked out. So now let's begin using this information to identify what the torque is at the inner and outer cylinders. So let's begin at the inner cylinder. So that's going to be the force at the inner cylinder times the radius at the inner cylinder, which is the inner cylinder radius. And then the force at the inner radius is just going to be the shear stress at the inner radius times the area at the inner radius times the inner radius. And so the shear stress is just the viscosity times the shear rate at the inner radius times the area at the inner radius times the inner radius. So plugging this information in for that, as well as this information in for the shear rate, we are left with the torque at the inner radius equals the viscosity times -2 times the angular frequency divided by 1 minus the proportion between the inner and outer radii squared times the area at the inner radius, so that's going to be 2 pi times the inner radius times the height times the inner radius. So this belongs to the area, this belongs to the shear rate, and then we just move the inner radius down and the viscosity down. And simplifying this a bit, we are left with -4 pi times the inner radius squared times the angular frequency times the viscosity times the height divided by 1 minus the proportion between inner and outer radii squared. So that's the torque at the inner radius. Now if we go and define the torque at the outer radius, we have the force at the outer radius times the outer radius. And using what we know about force, we have the force equals the shear stress at the outer radius times the area at the outer radius times the outer radius, which is from this torque equation. And knowing what we know about shear stress, we can define it as the viscosity times the shear rate at the outer radius times the area at the outer radius times the outer radius. And plugging in what we found for the shear rate at the outer radius, we have viscosity times -2 times the angular frequency times the proportion between the inner and outer radii squared divided by 1 minus this proportion squared times the area, so that's going to be 2 pi times the outer radius times the height times the outer radius. So again, this quantity here is the shear rate, and this quantity here is the area, and we just move viscosity and the outer radius down. So we are left with the torque at the outer radius equals -4 times pi times the outer radius, times the proportion between the inner and outer radii squared times the outer radius squared times the viscosity times the height divided by 1 minus this proportion between inner and outer radii squared. And so if we take these two equations, the torque for the inner radius and the torque for the outer radius, and we set them equal with one another. We can do that over here. We have negative, so torque at the inner radius, setting it equal to the torque at the outer radius. We have negative 4 pi times the inner radius squared times the angular frequency times the viscosity times the height divided by 1 minus the proportion between inner and outer radii squared is equal to negative 4 times the pi times the proportion between inner and outer radii squared times the outer radii or radius squared times the viscosity times the height divided by 1 minus this proportion squared. So if we take a look at this 2 set equal to one another, we can cancel out a lot of very similar terms. And so we can cancel out this negative 4, this pi, this angular frequency, which is here. I just accidentally forgot to include it. It's my bad. So cancel out the angular frequency. We can cancel out the viscosity, cancel out the height. And so what we are left with is the inner radius squared equals the proportion between inner and outer radii squared times the outer radius squared, and then divided by both sides divided by 1 minus this proportion squared, which in theory would cancel out. So we're left with the inner radius squared equals the proportion between inner and outer radius squared times the outer radius squared. And this, again, works because we earlier defined that this k value times r is just the inner radius. So if we plug this in for this radius over here, this inner radius over here, we have the proportion between inner and outer radii times the outer radius squared equals the proportion between inner and outer radii squared times the outer radius squared. And so if we look, these two are equal. So what that means is that the torque on the inner and outer cylindrical surfaces are equal.